I'm sure we'll have people trickle in. So maybe let me give a long intro, and then this will give people the the chance to come in. Okay, so welcome to another episode of GPU Mode, everyone. Like today, I'm actually super thrilled. Like we have Jay Shah on the call, who's here to talk to us about Cutlass and flash attention. Um, the way I first had heard of Jay was like I'd been following Hill on Twitter, who's like also an avid chess player, and I asked him like, who should we really invite to come give like an interesting talk about CUDA and Cutlass, and the first name that came up was Jay. After that, like I went down like a deep rabbit hole reading Jay's blog. So Jay's blog is and company is called Colfax Research, and they do lots of interesting work at the intersection of math and performance. It is so far, I think if I were to look at like just blog content wise in terms of like the quality of the overall content, I think it really rivals the best stuff, like basically things like Simon Bohm's articles. And I really enjoyed it. It was like very intuitive, like very thinky, very elegant. And so I'm like super really thrilled to have Jay here. So earlier in the call, he also shared like a very interesting tidbit that like Colfax Research is actually a family business. And it's a family business that mostly deals with like doing math and performance programming. So the most unique family business I've ever heard. So yeah, without further ado, Jay, please take the stage. Again, it's a pleasure to have you here.
Jay, I want to add one more sentence. Most of your blogs we have read in as part of the rewrite of the PMPP textbook, and we will be incorporating many of the content that you have shared. So thank you so much.
Oh, I'm thrilled to hear it. Thanks. So I'm going to let me share my slides, of course. So today I'm going to talk about Cutlass and flash attention free. And here's the plan for the talk. I'll give a quick recap of attention and the key ideas of flash attention. Then I'll give a high-level overview of the flash attention free algorithm. And this is meant to set the stage for what I consider to be the most the greatest value that you might gain from this talk, which is me then giving a deep dive basically into how you might code up the algorithm. So how you translate the algorithm into working code built on Cutlass. At which point I'll switch over to my coding environment. So what is attention? Attention is the key component of the transformer architecture. And it involves this formula O equals softmax Q times K transpose times V. So I start with my query and key matrices, M by D and N by D. They're drawn like rectangles because D is typically much shorter than the sequence length. And from this, I compute this matrix product, which is meant to record the similarity scores of comparing the query against the key tensor. And this is some M by N matrix, which is much larger than Q and K. I then take the row-wise normalized similarity score, the attention probabilities, by taking the row-wise softmax of this scores matrix. Softmax is given by the following formula. I then multiply by the value matrix, and I end with this this output matrix that I then write out and as the output of attention. So attention scales quadratically in the sequence length n, making it the key bottleneck to long context applications. The naive algorithm, if you want to actually implement this on the GPU, you can load K and Q and K by blocks from high bandwidth memory, global memory, compute S, but then you have to write out S to HBM in order to compute softmax on it, because softmax involves the a priori global knowledge of the rows. So this involves this intermediate write and read of the attention, the scores matrix to HBM. That causes naive attention to be bottlenecked by memory reads and writes because of the size, first of all, of the scores matrix and the slowness of reading and writing from HBM as compared to working on chip. To understand that, I'm sure many people in the audience are familiar with the memory hierarchy on the GPU. But at the time, when these ideas were being developed, this was not so common. This was not really common knowledge to people, at least working in machine learning. So in terms of the memory hierarchy, the key thing is that there's an inverse relationship between the size of the memory and the speed, the bandwidth. At the lowest level of the memory hierarchy or pyramid, as depicted here, you have HBM, i.e. global memory. And then at a higher level, at the apex of the pyramid, you have shared memory and moreover on-chip registers, which has a much smaller capacity, but as a trade-off, you have a much higher bandwidth. So you have to, the idea behind flash attention was that you have to exploit the memory hierarchy in order to speed up the algorithm, and in particular, not materialize the intermediate scores matrix to high bandwidth memory. So the idea in flash attention was to leverage tiling and recomputation to speed up attention. So as mentioned, I don't want to materialize this S matrix to HBM. As a consequence, or relatedly, I have to compute softmax normalization without access to the full input, the full rows of the scores matrix. And as a second challenge, for the backward pass, I have to since I'm not materializing the scores matrix to HBM, I have to compute it without having that attention matrix computed in the forward pass. To solve this, we use the classic technique of kernel fusion. We want to fuse all of the computation done in attention into a single kernel notch, using tiling and the online softmax idea to get around having to compute softmax normalization. So for flash attention, for a given tile of Q, as depicted earlier, you want to load tiles of K and V block by block and accumulate values of the corresponding tile of O, computing the intermediate S and P using online softmax and rescaling O as you load K and V block by block. You also leverage recomputation in the backward pass to avoid having to store the attention matrix. The flash attention 2 algorithm is presented on this slide. So as mentioned, I have to load Q block using a blocking of the entire query tensor into shared memory. The block size I call BM here. And then for over tiles of K, I have a separate block size tiling K with which I call BN here. And I load that also into shared memory. Then I do my first gem, computing S, taking Q times K transpose and scaling by the head dimension. I then track some statistics, such as the row max, which I need to do softmax safely because it involves an exponential, as well as the row sum to eventually normalize. And I also I do the exponentiation of these intermediate matrices and load V correspondingly and do that multiplication, as well as updating the accumulator as I go through the loop. In this way, the flash attention 2 algorithm can compute for a given query tile, Qi, the corresponding output tile, Oi, and write it out to HBM. The outer loop is parallelized in terms of the launching Fred blocks, and the inner loop is what we call the attention main loop per Fred block or per CTA. So that's a great algorithm, and it's essentially optimal on A100. So you have to talk about always in this sort of story with hardware-aware algorithms, the hardware that it actually runs on. And for A100, flash attention 2 is essentially optimal. It reaches around 80% utilization. However, on H100, it's very far from optimal. Note that you see numbers in the mid 300s here, but the theoretical max teraflops is about 1,000 on the H100 SXM5. Here, I'm not using the new Hopper instructions, WGMMA for doing matrix multiplication and TMA for loading from global memory. As a consequence, and because I don't use some advanced ideas that are necessary on Hopper to get good performance related to asynchrony, I can only get up to 40% utilization with flash attention 2. So enter flash attention free. So this is a collaboration between myself, Ganesh Vikshandi, Ying Zhang, Vijay Thakur, Pradeep Ramani, and Tri Dao. So there are 3 core ideas for flash attention free, which we leverage to improve the performance on the H100 GPU. First, we use the new instructions on the H100, namely WGMMA, which is the higher throughput MMA primitive, fully asynchronous and collectively executed by a warp group, namely 4 contiguous warps, and TMA, which is the asynchronous load issued from a single thread newly introduced on Hopper, which accelerates the memory transfer to get the tiles into shared memory. Second, we leverage asynchrony in a sophisticated manner. We have both inter-warp group overlapping. This involves warp specialization to divide the warps into producer and consumer roles, as well as ping-pong scheduling, and intra-warp group overlapping per consumer warp group to overlap the softmax, namely the exponentials in softmax, with the asynchronous matmul. Thirdly, we not only improve the performance of the BF16 attention kernel, but also introduce low precision into attention. So we have FP8 for doing matmuls now in attention. This introduces challenges related to layout conformance to successfully invoke the FP8 WGMMAs, for which we need to leverage the idea of transposing V in the producer warp group after it's loaded into shared memory. We call this the in-kernel transpose of V. So in this talk, I'm not going to discuss issues related to the quality of the FP8 attention kernel, namely the sort of how you mitigate the accuracy loss that you expect from moving to low precision. The upshot is that we get, in the BF16 case, up to a 3x speed up over flash attention 2. And we have an essentially optimal implementation reaching up to 85% utilization, competitive with the best gem kernels for the attention kernel. So let me walk through these optimizations in order. First, we use the new instructions, WGMMA and TMA. WGMMA is necessary on Hopper to reach peak throughput, as compared to MMA sync, which is the Ampere instruction, which can only reach 2/3 of the peak throughput in terms of the theoretical maximum teraflops. TMA is this new model for doing loads from global memory. On SM80, on Ampere, we already had asynchronous loads in the form of CPA sync, but the TMA model is an improvement over the CPA sync model in that it reduces the uses of registers to do the address calculation. So this is handled by a special hardware unit. This saves registers. And in the TMA model, the TMA load, and there's also an asynchronous store, the TMA instructions are issued by a single thread, and they execute asynchronously in the proxy, the async proxy. WGMMA and TMA, doing compute and load respectively, naturally integrate into a producer-consumer warp specialized pipeline design, which I hope to discuss with reference to the code later on. Moreover, on Hopper, you have the certain warp group-wide register reallocation instructions. This allows you to give the consumers a greater share of the total registers in the thread block. So this is necessary to allow in particular for attention kernel, to avoid register spilling with the computation. So here's the CTA view of the flash attention free algorithm, where I have not yet put in the asynchronous, the more advanced asynchrony ideas related to the consumer. So this is just flash attention 2 with warp specialization. And this algorithm 1 is taken from our flash attention free paper. So I'm not intending to, of course, have you fully digest the slide before I move on. But the main thing I want to illustrate is that on line 2 and line 11, I have this producer-consumer separation. So I explicitly, in this algorithm write-up, initialize, I say that I initialize a certain pipeline object, which manages the necessary barrier synchronization between producer and consumer with a S-stage circular shared memory buffer. And the producer warp group is responsible for loading the data from global memory to shared memory. So the QI that I have to load in the prologue before I go into the attention main loop, as well as the loads of K and V loading all of K and V for that to execute the computation of OI for that QI tile. On the other hand, in the consumer main loop, in the consumer path, I wait at various places on the producer loads to complete, and then I have the same algorithm as before with flash attention 2, essentially, at this stage. So in terms of the SM80 implementation of flash attention 2, this was not how that was implemented. So if you look at the flash attention 2 code, there is not warp specialization to divide producer and consumer. So this is something that is new in flash attention 3. In fact, in SM80, the flash attention 2 implementation there already used CP async to asynchronously load tiles from global memory. However, for Ampere style kernels like flash attention 2 and gem kernels, in fact, typically a multi-stage design where you interleave consumer and producer within the same warps is more optimal. But we instead on Hopper, we want to use warp specialization for FA3.
Jay, may I ask a couple of questions?
Sure.
So what was the insight to do warp specialization? So I'm trying to understand, why did you go in that path? First question. And the second question is, why did you pick warp specialization of 2 level? You could have done 3, right? So you could have done the loading as one, computation as another, and writing as third one too. So I'm trying to understand what was the insight behind picking up the 2, and also why specialization. So.
Sure. So initially, we actually, in our first implementation of flash attention on Hopper architecture, we used a multi-stage design where the producer and consumers were interleaved in using the same warps to do both loads and MMA. So essentially what we did is we took FA2 and we replaced the CP async with TMA and the MMA with WGMMA. And that already yielded a substantial improvement. We were motivated then by the fastest Hopper gem kernels using warp specialization. So at some point, we had both a multi-stage flash attention kernel as well as a warp specialized one. And we compared them, and we were able to extract a certain improvement with the warp specialized kernel. So that's basically, it led to us essentially adopting the warp specialized design for all of the attention kernels that are fastest on Hopper.
Why pick 2 level and not 3?
So by 3 levels, do you mean I have another warp group for doing the stores?
Yes.
So for doing the stores, you want to store using the consumer warp group because you accumulate in the registers. So I don't want to store to shared memory and then have a different, there would be no real point to store to shared memory. You have to do the consumer warp group and then issue the TMA store from a different warp. You might as well just issue it in the consumer warps.
Okay.
Like TMA, yeah, right. So the benefit of warp specialization is having the compiler better optimize and interleave the loads in the main loop with the compute. But the store is issued once at the end. So there would be no benefit from having the producer do the store.
Yeah, store is not blocking for you. So I clearly understand. So thank you.
Sure. Yeah.
Yeah, I have a question about that I thought I would put in now since Vikram just asked that good question. it's just like sometimes I think about the warp specialization that it's partly a tool to be able to reason about how many threads are doing like non-load stuff at any given time. And I wonder if that's something that you've thought about, or if that's accurate in some way, which is like if you just have one warp allocated to do these like load issuing instructions, then you know that like all the other like, n minus 32 threads are active doing like computations at a given time. And you can reason maybe better about like saturating the GPU. But on the other hand, like if you're doing this cooperative thing that you were just talking about, like you're like, wait, at this moment, maybe 3 warps are busy issuing loads, and at this other moment, do you know what I mean?
It's certainly, so from a legibility perspective and simple, you're just being able to write code more efficiently and in a simpler fashion. It's warp specialization is way easier to read and to reason about. Yeah, I agree with that. So the other thing is that you can, so does that answer the question? Yeah, so it's easier to write warp specialized code, just straight up.
And I guess because the TMA unit is actually doing the work, it makes sense that like all you're really doing with this one kind of dummy warp that is the load warp is just issuing instructions and then kind of being done.
Yes, exactly. So for example, we actually, so there's going to be a caveat to that. You can actually use the other free warps in the producer warp group to do stuff, to do sort of pre-processing like the in-kernel transpose that I talked about. So that'll play an important role for the FP8 kernel. But yeah, that's essentially right. The reason we have a producer warp group here is to be able to use the register reallocation, which only operates warp group wide, even if you only use one producer warp.
Oh, I see. Okay, that's something I should think more about.
So that's why we say if in the producer warp group. So really, yeah, we're going to, for the BF16 kernel at least, once you're in the producer warp group, if you're in the last free producer warps, you just return after doing the reallocation.
Oh, right. And deallocation, if I understand correctly, is saying I don't need these. Somebody else use them.
Yes, you free them up and then you reallocate them to the consumer. So otherwise they would be equally split.
So Cameron in chat is also asking, warp specialization does warp specialization also pass instruction scheduling to the warp scheduler instead of the compiler trying to interleave producer and consumer ops?
So the warp schedulers are still deciding at the cycle level what instructions to execute. Like, so all you're doing with warp specialization is that you're making the compiler's job. So I think of it as making the compiler's job easier, or the warp scheduler's job easier, because the producer warp, it's only the only thing that the warp, which is labeled producer warp, does is it just issues TMAs. That's its only job. And that should, so if you understand how the compiler works, which to be quite honest, I don't have a deep knowledge of the compiler because it's a black box. But if you believe what you read about how the compiler works, then it will be able to better interleave loads and compute instructions because of this, because you wrote warp specialized code.
And also it increases your coalescing effectiveness. So when you do your warp specialization, your memory access pattern becomes more improved. So.
Sure. Any other questions?
No, that was a fun side quest. You should keep going.
So this is FA2 plus warp specialization with TMA and WGMMA. That already gets you very far, but we can improve on this. What the? Sorry. Okay. Yes. So with asynchrony, we can use that. Well, first, here's the problem. So the special functions used in softmax are very low throughput. As a concrete example, let's say I was in head dimension 128 and I block size 128 by 192. FP16 WGMMA would have execute over twice the cycles as the special functions. So the proportion is actually quite large, unexpectedly large, you might imagine, in terms of looking at the exponential. It's even worse for FP8, where it's actually would be equal. They would take an equal number of cycles. And if you want to improve the speed of the attention kernel, you want to use the fact that these are using different hardware units, the tensor cores versus the SMPTE cores, in order to and try to overlap these instructions in order to improve the overall speed. So we want to be doing exponential, in other words, while tensor cores are busy with WGMMA and using that the tensor cores execute asynchronously. So the first thing we could try doing is just in terms of the different warps, in terms of the different warp groups, really, because one warp group collectively executes a WGMMA. And for this, well, you can just leave it to some extent to the warp schedulers to elect which instructions to execute. But we can actually improve on just what the warp schedulers by default do for us in terms of explicitly via barriers organizing the execution flow of the attention computation. So, for example, if we have two compute warp groups, two consumer warp groups, we could schedule the WGMMA of warp group 2 under the softmax of warp group 1, as illustrated in this picture. So this is an idealized picture, but we can, to some extent, approximate this execution schedule using barriers. And we call this a ping-pong schedule. It's very similar to the idea of ping-pong scheduling in the GEM kernel. So in practice, this often yields some speed up. So this is some hypothetical. Well, I mean, this is not. I mean, sorry. It's under certain conditions you can observe a speed up like this, and these numbers were observed for a certain configuration, but we're planning actually to put in the code a separate path where you can sort of easily disable ping-pong scheduling for doing ablation studies like this. So the numbers themselves shouldn't be taken too seriously, but in practice, you do observe for certain configurations a speed up using ping-pong scheduling. So that's something that is fairly simple to implement, but within a warp group, you can also overlap softmax and WGMMA in the sense of this picture. So this is something we'll look in the code later on in order to understand how to exactly implement this. But what's going on here is that I have to break the dependencies implicit in the attention computation, where I do my first gem to get the scores tile. I then do softmax on that output, and I feed that into the second gem. Well, instead of doing that, I can maintain a separate register buffer and have softmax execute on the prior stored register buffer overlapped with the first gem for the next iteration of the main loop. So I label iterations by numbers here, and you can see how WGMMA 0 is overlapped with softmax of the prior scores tile. Again, this is an idealized visualization of the schedule, but this is how we think about it being executed. And of course, maintaining a separate register buffer to store the scores of the prior iteration is going to increase register pressure. So this is not something that you may always want to do, but in practice, we do observe an increase in the teraflops if you use if you use a scheme like this. So here's the full flash attention-free algorithm incorporating the prior ideas about asynchrony for BF16 or FP16 precision viewed in the consumer. And in this algorithm, which I extracted from the flash attention-free paper, the thing I want to emphasize is how we're explicit about when we issue a WGMMA versus when it completes. So we are issuing these asynchronous matmols, and we issue them and we continue with the computation. And at some point, we have to wait for them to complete. So if you look at the main loop, for instance, I have this S next equals Q times K. And I issue that. I then do the computation of the next gem. I issue that again asynchronously. And I wait for the first gem to complete. And then the second gem is then overlapped with the softmax. So I think that this might be, sorry. I hid the line which computes softmax. So this is a slightly obscured algorithm. Perhaps the prior visualization is better. I should improve my description here. But the idea is that, as we'll see in the code, that you can decouple the completion of the matmul from its issuance. And if you're careful about managing the dependencies between the softmax and the matmul, then you'll be able to implement this algorithm without triggering a serialization warning that the compiler will produce if there are dependencies that are unaccounted for in your when you write down these when you write down this code. So this will be I think better. Sorry, it will be better explained when I actually look at the code. So for the FP8 precision, you double the WGMMA throughput, but you trade off in accuracy. And for FP8, there are certain layout conformance challenges related to FP8, and I want to discuss those briefly, because those are, in some sense, the most interesting part of the algorithm is dealing with these challenges. So for the FP8 WGMMA, it turns out that you have a certain layout conformance requirement where you have to be memory contiguous in the inner dimension. On the other hand, for the QKV tensors, they're usually stipulated in global memory to be memory contiguous in the head dimension. That is the last, the D of the BSHD format. So this is B for batch, S for sequence length, H for number of heads, and D for head dimension. And when you load using TMA from global memory to shared memory, you can't change the contiguous mode. So there's a certain restriction on TMA with respect to this. For gem 0, this is fine as is, because I have Q times K transpose, and you'll note that the inner dimension is the head dimension. That's the one that's the dimension you're contracting for the matmul. However, for gem 1, the head dimension for V is not the inner dimension. So you have to transpose V in terms of memory in order to use FP8 WGMMA. And the solution here is to do an in-kernel transpose of V in the producer warp group. And at a technical level, you can use LDSM, STSM instructions to do this with a very few number of registers for loading and storing from shared memory to registers. And you have to specify these copy instructions with custom layouts. It's quite complicated, actually, and do some register movements using byte permute in between. I will not elaborate on this, but if you look at the code, you'll note that this the layouts that we choose are tailor-made to this problem. So it's a very customized piece of code that you have to write to accomplish this. Moreover, on the consumer side, you have to reshape the accumulator layout for the first gem to the operand A layout of the second gem. So we have Q times K transpose. I have I hold the value of that in registers. I do exponentiation in place on that for the online softmax step. for the P tile that I feed into the second gem, and that's held in registers, and the WGMMA sources there its first operand from registers. But WGMMA has a certain layout requirement on the first operand, so you have to do a certain reshaping operation. And that's illustrated in this figure. So you have to know, to successfully implement this algorithm, the assumption that WGMMA makes in terms of the thread ownership of the values of the tile. If the assumption is violated, as it is for converting from FP32 to FP8, you have to do some register movements to ensure that it's satisfied. And as an interesting technical note, in the FP8 algorithm, the in-kernel transpose of V actually writes out a row permutation of V, which allows you to actually avoid certain shuffle instructions for the P matrix. So instead of multiplying P by V, you're multiplying a column permutation of P by a row permutation of V. In this sense, there's some certain cleverness involved in setting up the FP8 attention computation. So the final improvement, optimization I want to discuss before we look at the code is the use of persistent kernels with flash attention. So just like with gem kernels, you want, or you can, decouple the physical CTAs that are launched from the logical work tiles. In the persistent kernel, you launch a fixed number of CTAs to occupy the entire GPU, let's say equal to the number of SMs or streaming multiprocessors, and you can assign to each persistent CTA a number of work tiles. This allows you to overlap the epilogue of a work tile with the prologue of the next, in particular with the TMA store that writes out the attention output, and the prologue loads for loading Q and K for the first WGMMA for the next work tile. As an example, let's say I have sequence length 4K and 8 heads and 4 batches. And my block M is 128 because of how WGMMA works. So I have 32 M blocks. So this would be 32 times 8 times 4 is 1,024 work tiles that I process in the kernel. Without the persistent kernel, I would launch 1,024 CTAs, and I have a one-to-one mapping of CTAs with work tiles. With a persistent kernel, I launch, let's say on SXM5, 132 CTAs, because those are the number of SMs. And for the attention computation, I have to use all of the resources of an SM to process a work tile because because the computation is so heavy. This is the same as with a Hopper gem kernel, by the way. Then in the persistent kernel, each CTA would run over a certain fraction of the total number of work tiles. And I would be able to do this prologue epilogue overlapping that I discussed. Moreover, you can leverage dynamic allocation of work tiles to the next CTA in the persistent kernel to help with load balancing issues where not all work tiles are processed at equal speed. So for instance, when doing causal masking, this helps with the load balancing, considerations involved in causal masking. And in practice, it is quite important to use a persistent kernel. So what's the speed up in total that we get? We get, in the most important case of head dimension 128, up to 750 teraflops without causal masking, and about 700 with causal masking currently.
Hey, Jay, could I ask a question, please?
Yes.
Can you clarify, when you talk about persistent kernels, can you clarify what's special about the stream K framework there? Is it an entirely different? I mean, to me, it seems very similar, but I'm not always clear about exactly what demarcates the two.
Stream K requires persistent kernels, but it's
Right.
It's a certain way of scheduling the work tiles.
Oh, okay. So it's like it's a scheduling algorithm. Okay, thank you.
Right. Yeah. So using a persistent kernel makes it simpler to decide which scheduling algorithm I want to use.
Right. And this is the thing where you see the template argument like tile scheduler, right? That's like you could put stream K or.
Yes, exactly.
Thank you.
So we get up to 700, up to 85% utilization with head dimension 256, for which it's an easier problem than for lower head dimensions to fully utilize the GPU. And for FP8, up to 1.3 petaflops. And I want to highlight now, advertise maybe, a certain improvement that we discovered for FA3 with inference. So let me first look at this chart. So with if BF16 data type, and in a multi-query attention setup where I have 16 query heads and 1 KV head, I can find a dramatic improvement over flash attention 2 in a memory bound regime. So where the query sequence length is a lot shorter, as it is for decoding, than the context length. The context length and the batch size is listed on the bottom x-axis. And you can see that flash attention 3, the way in which we set it up currently, yields about a 6 to 7x speed up over flash attention 2. And it's more or less constant, well, for both, as a function of the product of the context length and the batch size. In particular, increasing the context length doesn't yield depreciation for the in terms of the bandwidth of the kernel. So why is this, right? So how could I find in the memory bound regime a huge improvement over FA2, which is a bit surprising because it's not really about WGMMA at that point. The idea here is that in this decoding setup, where query length is short, like a few tokens, and context length is long, we can do two optimizations. So first, just like in FA2, we can split along the KV sequence length to fully occupy the GPU. Optimization 1 is what allows us to have the time be constant as a function of the product of the context length and the batch size. So it's decoupled from the context length, and it's just about bytes. The second optimization is something that we didn't do in FA2 yet, where you can pack in a GQA or MQA setup multiple query heads into a single query tile, because you have your WGMMA tile, which is fixed as a multiple of 64 for the first operand. If you don't pack multiple query heads, you're launching more work tiles, logical thread blocks, and for which each thread block is not using most of its query tile. If you have a large batch size, then you're launching essentially nx additional waves, where n is the GQA ratio, as you would otherwise if you pack multiple query heads into a single query tile. And in this chart here, I chose these numbers very carefully. I have an MQA ratio of 16, a query sequence length of 4, its product is 64, which fills out exactly one WGMMA tile. So in this way, I'm able to get a 6 to 7x speed up in the decoding regime for flash attention 3. So in summary, what have I discussed? I've explained how flash attention 3 is optimized on Hopper architecture. The key ideas behind it involving asynchrony at every level and low precision for FP8. For inference, you have some additional tricks, split KV, which works the same as an FA2. So I didn't really explain how it works, but you can look it up if interested. It goes by this name of flash decoding, and this GQA packing idea to pack multiple query heads into a single query tile. That's tied to this this width of 64, which is special for WGMMA. The upshot is faster training, faster inference also, and better models with longer sequences. And the code, as we'll discuss shortly, can be viewed on our GitHub. So now for the practical portion of this talk. So we implement this idea of this algorithm using Cutlass. So Cutlass is built, we build on top of Cutlass, and it's essentially, it's inseparable in some sense from Cutlass. It would be extremely difficult to actually code this idea up without a sufficiently powerful library, at least akin to Cutlass. So let me discuss, before I look at the code proper, the overall structure of the kernel. So a Cutlass kernel, like with a gem kernel, but we use the same structure for attention, comes with three classes. We have a collective main loop to which we delegate the load and the MMA operations, or the load, in our case, the compute. A collective epilogue for doing store, and a tile scheduler to manage the work loop, which is important when using a persistent kernel to assign the CTA the work tiles that it operates over. And each class has its own set of kernel parameters. You pass them in the host using this two underlying arguments function. And I won't discuss the mechanics of that. Suffice it to say that you have to, from the host to the device, have some sort of clean way of passing all of the parameters you need to do your work.
Jay, could I ask a question here?
Yes.
So I've noticed that with successive versions of Flash Attention, it's in a way, it's like the Flash Attention 3 repo is like a mini version of Cutlass. Like it has a lot of the same building blocks and stuff. And it almost seems like Cutlass is sort of a new CUDA C++ like programming paradigm in a way. I don't know if that's the way you think of it, or I thought you maybe would have something to add to that.
So it has certain ideas for which are built into the library, but I don't really think of it as its own. I mean, you can say it's a DSL, I guess, but it is. I wouldn't view it in those terms personally.
Okay.
So it manages. So the Cutlass allows you to intelligently manage the mapping of threads to data, and it has certain abstractions for handling this for you. But I maybe it's a matter of opinion. I wouldn't go that far.
Yeah, I didn't mean to make too strong a claim. I was just sort of, it's interesting that that the sort of way that it's carved up seems to have been pretty stable, like over the last couple of years. Like it's
So Cutlass 3, when we rewrote, we made sure that it becomes more conformal to the CUDA C++ model. So SYCL, CUDA C++, Cutlass, Qt are all modern C++ GPU programming methods that we have been building on.
okay, so it's even deeper than just Cutlass.
It's even deeper than Cutlass.
Yeah.
So the idea here is that each of this is actually designed for a very specific set of tasks, but also as a together, you actually get the everything as a package. So specialization is the way in which we make the most of performance over here. So
template specialization. Yeah. Thank you.
It is a deeply templated library, certainly.
I mean, you hate C++ for some reasons, but you love C++ for some reason.
So in the Cutlass, at least the clean way of designing a Cutlass kernel, you have these three classes to which you around which you organize the kernel. And in this producer consumer warp specialized design, you have that the producer has the collective main loop do the loads. The consumer has the collective main loop do the MMA, or the compute more broadly, and then the store. And the scheduler manages the work tiles. So you have these two what we call work loops in the producer and consumer, handling load and compute plus store respectively. And let me now share my coding environment. So I want to take the consumer, the MMA method, and investigate that carefully. And I will show how you can use Cutlass, build on top of Cutlass to implement the ideas involved in the consumer part of the Flash Attention Free kernel for BF16. So let me move over. So, so let me maybe briefly indicate that we have our flash attention, the CTA view of the flash attention kernel. So it starts here, where I set up a bunch of things related to the pipelining, and I initialize the pipeline objects and the collective main loop and collective epilogue. I sync threads, and then I separate into producer and consumers. So I have my producer warp group. I invoke the relevant Cutlass method to do the register deallocation. I set up more pipeline auxiliary objects, which I won't have time really to explain in this talk. I initialize the scheduler, and I have my work loop here. So I have this work tile info class object returned by the scheduler with this get initial work method. I run over the for loop until it's no longer valid, with each iteration getting the next work tile. I fetch the block coordinate, the logical thread block coordinates from the work tile. I have some early exit logic, but the main thing here is the load method. So I have this collective main loop load, which is responsible for doing the TMA loads. And then in the consumer path, I have the register allocation with the MMA register requirement, the scheduler, and some initialization logic, and then the work loop. It looks the same, but in this case, I have here my accumulator TORO. That's passed to, and my softmax struct, which is responsible for doing softmax. I fetch the block coordinate. I use my collective main loop MMA method to do the computation, after which TORO has the values that I want to store. Then I call the store method. So this is the overall skeleton, or I would say at the CTA level of the attention kernel. My plan in this talk was to describe the MMA method specifically, but maybe I can ask if there are any questions about what I've just discussed.
So sorry, what is TORO?
Yes, so that's a good point. This is a Cutlass notation. I should have said that. So I have this. This is essentially going to be to put a long story short, the threadwise accumulator for the attention output. So the O is meant to signify that it's the O matrix. The R is that it's stored in registers, and the T is that it's the threadwise view. So this is a tensor, a register-backed tensor I create using this method here, which knows about the WGMMA layout. I create it as my, and it will be housing the values of the attention computation. It will be the accumulator.
I have a question, if you don't mind. So when this is like, I was asked a question about this naming convention in Cutlass, where you have things like you said, like TORO. I sometimes think of the first part of it. So obviously there's like two parts just juxtaposed, right? I sometimes think of the first part as like a task. Like the TO is like a task, and then the RO is like, here's the view of the register memory RO needed for this task. But I don't know if that's like how you think of it, or
I think of this this prefix as saying it's the thread level view of the data.
but sometimes you might say like so what does the first capital O mean to you? Like what is that part of it? The T for thread, right? But then what if it were TCRO or something? Would that be different?
So it's about the related maybe to the operation. I don't have a stringent I'm not so stringent with the nomenclature, to be quite honest. In this case, I duplicate O because it's related to the MMA. I could also put C here for it being the the accumulator C4 and MMA generically. But I think TORO is at least clearer for me.
Thanks. Yeah, just trying to get it clear in my mind there.
Yeah. So the things I won't explain so much are really the pipeline classes, because that's sort of its own topic. What I want to explain with this MMA method is taking that algorithm, in particular the intra-warpgroup gem softmax overlapping, and seeing how to implement that in Cutlass. So here's the MMA method, and I've tried to simplify it a bit, but not really so much. And let's step through what you need to know about Cutlass and what you need to know really about the algorithm in order to implement it. The first thing is the following. So first, in this sort of method, I set up the views of shared memory. And WGMMA sources its operands from shared memory, except possibly for the first operand. So let's remember in attention, what are the two gems? I have Q times K transpose and P times V. Q and K are loaded into shared memory. P will be something that I modify in place as the accumulator of the first gem. V is loaded into shared memory. So I won't explain in this talk about TMA part of this kernel, just the MMA part. So all I have to do here in this MMA method is to construct the views of the shared memory that I'm going to use in the gems. So in Cutlass, we have this in terms of the library. I can do this as follows. I have some location, in this case, some shared storage struct, which manages the pointers for the which houses all the data that I'm using in shared memory. I then have this make SMEM pointer method. I can pass it those these free objects in the shared storage struct, and construct a Cutlass tensor using that pointer and a certain layout. And these layouts are something that I construct using a Cutlass helper function. Because for the shared memory layouts, they have to conform in terms of invoking WGMMA to a certain specification. So I don't have any real freedom in choosing these layouts, apart from first the shape. The shape here is K block M by K head size. And likewise for K and for V, where I also have the third mode as the number of stages being used in the pipeline. Because this is something which you don't have so much freedom over, you can just delegate that to Cutlass. So Cutlass will produce the right layout for me using this SMEM selector function. So if I go to where this is defined, you'll see that being how it's done. Really, I construct the atom, which is sort of the minimal, it's the indivisible part of what I need to pass to WGMMA using this helper function. And then I take that atom and I replicate it over the desired shape, which is constructed, which is fetched using this tile shape MNK, which is K block M by K block N by K block K, or head size. So the first part, to summarize, of the first thing you do in this MMA method is to construct the shared memory tensors. And Cutlass automates most of this process for you. The thing that you just have to decide on is what these values k block m and k block n will be. K block m is somewhat fixed, so it's going to be a multiple of the WGMMA indivisible size, which is 64 for the operand A. K block n is something that you have a lot of control over, and that's going to be something you tune based on the head size in terms of performance and the register usage of the kernel. So this sort of preparation is something you would see also in the Cutlass gem kernels in terms of the shared memory tensors. The next thing is to set up the MMA objects. So in Cutlass, you have this thing called a tiled MMA, which serves as your partitioner for preparing the tensor objects to be passed into the gem call. In this case, I build a tiled MMA for invoking WGMMA. So to do that, I use a Qt method called GMMA SSOps selector passed into the make tiled MMA method. This thing needs to know about the element types, both for the operands and the accumulator. In this case, for instance, bfloat 16 and float 32, the tile shapes, and the atom layout MNK, which is something which in our situation is related to the number of consumer warp groups you use. So if k block m is 128, then this is 211. And this is saying that I have, for the first warp group, it covers 64 by the other dimension, and the second one covers the other 64. This tiled MMA 0 is responsible for gem 0, or will be responsible, and this tiled MMA 1 will be responsible for gem 1. And in reality, I define these types above outside this method, but I just reproduce them here for clarity. So these are these cute tiled MMAs or Cutlass tiled MMAs. I initialize these objects, and I will use them to, in terms of rather the threadwise slice, to partition the shared memory tensors. Let me just point out that in my case, the tiled MMAs have to do with WGMMA, and the partitioners only depend. The only thing I need from them is really what warp group index I'm using. So I have this this warp group thread layout, which will get me the relevant slice, which is uniform per warp group, resulting in these WGMMAX objects, which I use to partition the shared memory tensors. In the Cutlass gem kernel, you might instead see, instead of WGMMA, you might see thread MMA. So these could also be thread-wise slices of the tiled MMA objects. But that's the general Cutlass paradigm. You have your tiled MMA type, and that can just be defined at compile time. I mean, it can be just defined. And then you have to pass in something about which is privy to the thread, the kernel information, so the thread index, in terms of the slice of the MMA object. In this case, it's the warp group. So I construct some warp group MMA 0 and warp group MMA 1, and I use these to prepare what are called descriptors to be passed into the gem calls. These are descriptors constructed on top of the shared memory tensors. So here I use these methods partition fragment A and B to do that.
Sorry for a dumb question. Does every thread have to hold a different descriptor, or is this only going to be
these? So this is each thread holds a descriptor, yes. So that's why I have a T here. It's just that the partitioner only depends on the warp group. But these, I mean, every line of this code is executed in the threads context. So that's part of the preparation. And this is very specific to WGMMA in terms of what I said about the descriptor. For other MMA operations, you would have what is called a fragment, or some sort of view of the shared memory, which is this thread-wise view. WGMMA has this other has a different model than most MMAs. In terms of Cutlass, though, it is treated uniformly thanks to overloading the method. Now I set up some consumer weight lambda that will be relevant for the pipelining, and I have to get coordinate data in order to know about where how I execute the attention calculation. The relevant coordinate data is fetched from the block coordinate parameter, which is passed into this method here. It's a tuple of 4 integers. So I have to know about the M block, the batch, the split index if I'm splitting the kernel. I use the batch to fetch the sequence length Q and K, which can vary from batch to batch. And I have to know where I start and stop in terms of reading K and V for N block min and N block max. I then have a separate masking utility here. So this, after I do that, I fetch the barrier, which is this transaction barrier for waiting on the Q load to complete. I have the option of loading Q in the consumer thanks to this code. It's not so important I'm not going to explain this, but suffice it to say that when I'm doing this patch GQA idea, I want to load Q using CPA sync instead of TMA. And I wait for Q to finish using this try wait method on the barrier. So this is more of the Cutlass, the very strong support that Cutlass has for managing synchronization. So you'll have to, if you want to set up this synchronization carefully, you'll have to be very familiar with operations like try wait on a Cutlass barrier object. If you look at, if I go here, you'll see that, maybe this will be this transaction barrier object. So let me not maybe delve into that. Now, I want to create a scores accumulator for storing the value of the first gem. So I do that here with partition fragment C. That uses the tiled MMA to have knowledge of the layout that I'm partitioning it over. So this will hold certain values as prescribed by the WGMMA operation for the output tile. In this case, it's K block M by K block N, because I'm selecting that from this shape object. I then wait, I've waited for Q to complete using this code here. I wait for K to complete using the consumer wait and the Cutlass pipeline. And now we get into the first gem. So I have this flash gem here, and that's a wrapper for the Cutlass gem. That takes in the tiled MMA object, and the descriptor on Q and on K with the relevant stage for K, since this has the last mode as its stage, and it accumulates in S. So this is the first gem call. This is, you can think of it as a prologue gem. Surrounding it is the ping-pong logic. So I'll revisit this at the end, but this is going to lock this is going to be the logic which implements that staggering in terms of between warp groups of the MMAs and the softmax. And this warp group weight, if I pass in -1 here, it's going to issue the WGMMA and not wait for its completion. So I have to explicitly say when I wait for its completion using this warp group wait method here. And this is something which syncs warp group wide.
I'm sorry, can you clarify the semantics of the -1? What is the negative?
So this is something which is special to our flash gem method, which essentially tells it to not wait. Otherwise, so warp group
Just a
wait,
flag then. Gotcha.
if I put n here, it would wait for the previous n commit groups to complete, up to n commit groups to complete. So there would be n trailing commit groups, excuse me. 0 means that there are no trailing commit groups waiting to complete.
Right. So you're sort of like, you're saying like, if you put in 3, you're saying wait for all but the last 3 to be done.
Yes, exactly.
Gotcha.
After which I can mask if I need. And I then create this auxiliary tensor for storing rescale values for rescaling O. So that's something involved with the softmax struct. And this online softmax method will do in-place online softmax on TSRS. I'm not going to discuss the details of this because this is some very customized piece of code, which is specific to softmax and not really specific to Cutlass per se, or doesn't involve Cutlass in some sort of essential way, I would say. Then I have to take S, which has now been converted to P, and prepare it to be used in Gem 1. And that preparation involves the following. So that's the point of this code. So if I'm FP8, I have to do some register movements. That's handled by these two methods here. That depends on, well, depending on whether V, I had to do in-kernel transpose of V. I have the option of doing offline transpose, like as pre-processing step. So that's why I have these two separate methods here. But apart from FP8, what do? I have tensor TORP, which is going to be my operand A for the second gem. It's going to be a register-backed tensor, which points to TSRS after I convert it, but with a different layout. So it's typical in the fused gem situation when I have the output of the first gem being fed into the second to have to do a reshaping operation, because there are assumptions that the MMA primitives like WGMMA make in terms of the layout, in terms of what threads own which values, and how the partitioner will present the thread-wise tensor. So you have to have a custom method typically for doing this, but this custom method involves Qt in an essential way, or rather, it's easy to build such methods using Qt and Cutlass. I pass the layout for the accumulator S, and I convert that into something suitable for being used in the gem call with the second gem. Then I prepare a big lambda for doing the compute step in the one step of the compute in the attention main loop. So let me explain this afterwards. I put that there. I then have something that I have to do with causal masking a few steps before I can ignore masking, in other words, that I can unroll. And I then have the actual attention compute main loop. So you'll note that all the logic has been kicked upstairs to the forward step, lambda. This thing just has to know about the end block that I'm working on. And these additional parameters are just they're passed as types. They're passed as objects whose types I can read. So it can be, these things can be converted into these constant expression Booleans for handling very special iterations of the forward step. But these special iterations are all are set to be trivial for the main loop that I do not enroll. So this is the heart of the algorithm, I would say. So let's try to explain it. There's some epilogue logic here, but you can ignore that. This is the thing that will reflect my asynchrony scheme in terms of overlapping. So here I have this n block. Let's just suppose it's not the first iteration. It's not checking that I possibly mask and I produce minus infinity. And it's not checking that I'm doing any masking. So I have to overlap in my asynchronous scheme. As we saw, I have to stagger the gems. So I haven't talked yet about pipelining really, but suffice it to say that this pipeline state class is a thread-wise object that knows about which phase and which stage of the pipeline I'm in. And here, I take this SMM pipe read V, which is used in the P times V gem. I create it using the current index of SMM pipe read, and then I increment SMM pipe read for my staggering. So that gem 0, it will be ahead of gem 1. I then create, again, the scores accumulator using my Cutlass method partition fragment C. I wait for my TMA load K to complete using the consumer wait method with the pipeline K and SMM pipe read. I have this ping-pong synchronization. And then I do gem 0 for the iteration n block -1. I'm reading from right to left, by the way, in my attention main loop, because with causal masking, I want to start on the diagonal. And I always just want to read from right to left because of that. So I do this gem here, and it uses the tiled MMA, Q, K, and S. I rescale O because of online softmax. And I wait for V to complete, and I then do gem 1. And I note that these two MMAs execute asynchronously because I've passed warp group wait -1 here, and I do not wait for either of them to complete so far. I then have warp group wait 1 here, which waits for this guy to complete. So here, at this point, Q times K transpose on the next iteration has completed. P times V is not supposed to complete, not known to complete. So it's potentially still executing. I then release K, thanks to K being finished with. I mask if needed. Here I'm not doing any masking if I pass in the no mask function. I copy my rescale data to score scale. I do online softmax. And this online softmax is done on the output TSRS of this flash gem here. So this guy is executing while this guy is executing potentially. And in practice, they're being interleaved if you examine the SAS code. Here, I ensure that the P times V completes, and then I release V. And then I do, again, this conversion, and I copy to TORP to be used in the next gem. So TORP is my register buffer that's being reused here. So this is gem 0, gem 1, softmax overlapped with gem 1. And that's the picture I was depicting in my slides. Any questions so far?
I had one simple one, which is like, as far as like the code goes, is this like in the DAO repo, or is this like your own fork? It looks like.
So this is in a separate branch that we're planning to integrate very soon.
Okay, very cool.
And
So-
what is, pardon me, what is the main like thrust of this branch? Is it adding a particular feature, or is it just
So it's adding some improvements to decoding.
oh
It's
great.
called Decode.
Oh, okay.
But I haven't explained it. I'm not going to explain any of that. It's also a general refactor to make the code cleaner. But it doesn't really do much for the base kernel, I would say.
I guess like the other question I have is like, I mean, like like even for like a simple function, like this is still quite complex. Like it's 1,000 lines. It's like very thinky. There's like a lot of like waits and async calls that are going on. And so I'm curious, like if you found any tools in the NVIDIA ecosystem useful to be able to debug async errors or like basically like memory corruption errors?
Unfortunately not. I mean, we have to I mean, you can use compute sanitizer, but that's not, I don't find that so useful, to be honest. No, I think you just have to think through it very carefully. And we have, a PyTest suite for checking race conditions and things like this.
Oh, I see. So it's very much a write the algorithm carefully first and then write the code kind of exercise, as opposed to sort of iteratively figure out how to make the code faster.
I think this is most of the time the old guys who used to do CUDA programming before the profilers came in. This is how we used to write the code. So I started doing the same like long time ago. Compute sanitizer is the least one we use.
So certainly, we spent a lot of time, certainly debugging things.
Yeah,
Uh,
print case. Prints, right? So that's the best debugging tool ever created. I noticed that in the main kernel versus the main repo versus the repo that you have a lot of comments. And thank you for adding those comments because the original repository, it was very hard to parse when I was going through those code base. But this is far more easier to parse.
Oh, and
Sure.
I should, sorry to interrupt, but Vikram made a good point, which is that a grid, if you're going through this code, there are often these commented print statements that you can uncomment to allow yourself to see some stuff that the writers, either it's Cutlass or Flash Attention, thinks that you might want to know. So that's useful.
So with this code, I think the other thing I want to explain, okay, so let's maybe go at the end here. At the end, I have, I do my final rescale, my final gem because I'm staggered. And I have my finalize method. The finalize method does the normalization with the sum at the end. It divides over the sum. And rather it copies the normalization number to score scale, and then I rescale that. So yeah, there's some epilogue logic, but rather tail logic. At the conclusion of this method, the TORO is ready to be written out without any further compute done to it. So that then the collective epilogue will store it to global memory. The final things I want to explain are, first, the ping-pong scheduling. I haven't touched that. Second, the flash gem method, what it wraps. So the flash gem is a wrapper around Qt gem with some WGMMA synchronization logic. And thirdly, the reshape operation. I think I will go maybe in reverse order. So let's first look at this flash convert accumulator A-regs, because this will give some indication of what you actually need to know in practice about these layouts. To a large extent, people say Cutlass, it's all about the layouts and tensors. But to a large extent, you can black box the layouts. You can just think about the shapes, because the strides are going to be determined using these helper functions, like I mentioned with this code here. The layouts being prepared to be compatible with WGMMA using just the standard Cutlass methods. And at that point, you don't really have to think about it. But you have to think about it in this one place where you're doing this reshaping operation. So let's look at that. Oops, sorry. So what am I doing here? I want to highlight this line here. So this here is going to be the layout for TSRS as an accumulator. And it looks a bit funny. It's 2, 2, n over 8, MMA M, MMA N. You can think of this MMA, the 2, 2, n over 8 as MMA V. So those are the values that are held for the accumulator in terms of the WGMMA atom. In this case, that atom is very large, actually. So you expect this MMA-M to be 1, because this is, well, let's just say that you expect these things to be 1. So this is, in Cutlass, they like to say that this is the value mode, and then these are the trailing, the tiling modes. When you take your partitioner and you partition something like a shared memory tensor or the an output tile, in this case, it will always produce something that looks like this. So you'll have your value mode and then the additional tiling modes. And the partitioners will partition something suitably to be inputted into something like a Qt gem call. However, in our case, I have a fused gem. The partitioner is something that when I use partition fragment C, it's doing that partitioning with respect to thinking of the tensor as an accumulator. But now I want to pass it in as an operand, and I want to do that on my, directly without the Cutlass partitioner. So that means that I have to write this reshaping utility. As the operand A of gem 1, this TSRS, this thing I want to do this convert layout on, should have value mode 2, 2, 2. Because here I'm thinking of M and N. Now I'm thinking of M and the inner dimension K generically. And but here for these modes, I have to pass, I compute them so that it has this this shape. This is a reshaping operation in the truest sense, in that it doesn't involve any actual register movement. It's just a change of the view. So with the FP8 layout conformance requirements, I actually have to change how the threads own the registers, potentially shuffling among threads, and in any case, always permuting the registers per thread in terms of their order. But this is simply a reshaping operation. The order is maintained in terms of each thread, and threads don't have to exchange data to do this. So that at least says why I have to go from point A to point B. How do I do that, this reshaping operation here? Well, I can just use the Cutlass this methods, including size, logical divide, make layout, getting the right values with my detailed knowledge of what it actually is, in order to produce the layout that I return here. So this is very low level. This is sort of the lowest level Cutlass code you would write. If you unpack it, it's very simple, but it is very low level. But I encourage you, if you want to think about a layout reshape problem in Cutlass, which shows up in a fused gem problem, look at this method here. Tree also wrote this. He uses this in FA2 to do a reshape in the SM80 case as well, in which case you have this sort of situation. So this is low-level Qt code, if you think of Qt as being the thing which handles layouts and tensors. Now, the second thing is to look at the flash gem. And I just want to look over that, excuse me, sorry, in order to discuss what is different between QGem and flash gem. So QGem is something that is written here. I have my A operand, B operand, C operand, my tile MMA, and all of this is passed to the QGem call to execute, in this case, the WGMMA instruction. But this is something which is through template specialization and overloading, it dispatches to the right MMA method, but it doesn't involve any synchronization as you would need with WGMMA. That's handled outside this method. So we wrap this in this flash gem method using some things which are specific to WGMMA, namely warp group fence operand, warp group arrive, and warp commit batch to commit the prior collection of WGMMA operations into a commit group, which is used in the warp group wait method. And the warp group wait is issued here if I pass in a valid integer. Otherwise, if I pass in -1 as before, it doesn't wait. The last thing I want to discuss is this ping-pong scheduling. With the ping-pong scheduling, it's handled via it's delegated to these two methods here. And this involves, if I look at what these do, this involves using the Cutlass arch name barrier sync to call bar sync, where I can specify the number of threads involved in the sync and what barrier ID I'm working on. So with the barrier arrive and barrier wait, the barrier arrive goes after the barrier wait. The barrier arrive goes after the barrier sync. The sync will block one of the warp groups from executing while allowing the other to pass through. The arrive on the warp group that passes through will then allow the warp group that was stopped to proceed. We handle this using named barriers. So the named barriers are offset from each other so that the scheme I described works. That's the point of describing these pairs here. So that's why for ping-pong scheduling, all I have to do in this case is just take this flash gem and bracket it using these two methods, which, in other words, this is, in a sense, it's much simpler than doing any intra-warp group overlapping. It's just putting name barriers in the right places. Okay, so I think that's what I wanted to discuss for today. I hope it was at least, somewhat helpful, at least. Of course, the flash attention code this is just one, though you could argue it's the most important method. It's a small, in terms of the lines of code component of the beast, which is the flash attention kernel. So there's a lot more that I could discuss, but I'm out of time essentially, unless people want me to explain other things in this kernel or explain more about this MMA method.
Thank you, Jay. This was fantastic. Like, I really appreciated the theory, the Pi stuff. I think you're the out of all the guests we've had, you've been the one who's dove into code the most. So thank you. Yeah, I mean, like as Jay said, if you have any questions, like please start posting them in the chat. I guess like one thing I was curious about asking you was like it does seem like a lot of your work is like around like wrestling complexity, like, and there's like multiple angles to it, just because like you're also depending on fairly new features that not a lot of people are using. They might not be as documented. They're harder to debug. And so I'm sort of curious, like where you get your like alpha, essentially. It seems like a big part of it is Cutlass, but I'd love to hear more.
So Cutlass, it's nearly impossible to code this up without Cutlass, essentially. It just does so much of the heavy lifting. But I would say the alpha is, so you could say there are two things, right? There's the thinking through the algorithm very carefully. So one big, I didn't discuss this in the practical part, but that trick with the GQA, what I call GQA packing, where it's just a simple idea, put multiple query heads into one query tile. So that's a hardware aware part of an algorithm because it's tied to specific shapes, namely the 64 involved in WGMMA. But that simple idea leads to like a 6x speedup in decoding. I mean, so they're simple. I think that, you can rapidly test out your ideas if you have a very robust library like Cutlass that can facilitate implementing them. But the idea in principle could be implemented without Cutlass. It's just impractical to do so. I would say I would really put I guess they're inextricable. It's sort of, but complementary.
I think you are right in saying Cutlass is more like a DSL, and that allows you to make much more fancier way of programming this TMA and the GEM operations into the GPU. I think that's the way in which I think of Cutlass too. So I do have one completely, I don't know whether you're working on this or not, so I'm just throwing this question to you. FP8 was a nightmare to make it work, right? What are your thoughts on making FP4 or MX4 or MX6 going forward, given that there's a lot of attention towards a much more smaller precision too? So do you think, or do you have any plans of looking at much more lower precision, because the complexity is even more higher over there? So
well, I think that the FP8, also from an algorithmic point of view, the hardest thing about FP8 is the in-kernel transpose.
yes.
So that's something you have to really, that's very specific to the layouts involved in FP8. And it's not like, so this code here is a lot of all the layout stuff is really, like, apart from the reshape that I pointed out, it's handled by Cutlass. You don't even have to think about it, basically. You just have to think about the shapes. I saw there was a comment in the chat about putting the strides, but it's really, you really just have to think about the shapes. And the partitioners will do all the work for you, apart from this one issue of the reshaping. That's not the case for FP8. And you have to think very carefully about the exact layouts involved, and then you have to write these tiled copies to copy shared memory to registers, and you can leverage algorithmic tricks like permuting your matrices and knowing that a product of matrices doesn't change under a matching row and column permutation, which is something we use here. FP4, I would have to, I would have to look very carefully at the hardware, the details involved in invoking the hardware level accelerated MMA instructions. It might be completely different from FP8. It might be very similar to FP8. I can't really say without having looked at it. But I would say that probably the very generic pattern of you, in the producer warp group, you load as, given how the data is laid out in global memory, which is forced upon you. You sort of don't have a choice. Let's say that in an API, if you want to support some API, you want to, people will give you the data in a certain format that is inalterable. Then you load it and you do your pre-processing in terms of this out of place transformation, which is in this case an inter-kernel transpose, in the producer work group. So that's one thing we learned, which maybe I should emphasize, that if you can also try, you stored it to shared memory, you can also in the consumer try doing this transpose, but it's going to be way worse than doing it in the producer. This is something we learned from CUDNN, that you want to do it in the producer to do this transpose. That lesson is most likely it's going to be applicable exactly the same as with FP4.
Mm-hmm.
But the specific the brass tacks of the layout transformation, what layout, how to solve the layout conformance challenge, the layout conformance requirements for FP4 is most likely going to be specific to FP4.
I think there is one more problem with FP4. FP4 is the Amdahl's law getting even more worse, right? So already in FP8, the exponent and the non-gem part was about 50%. When it comes to FP4 now, it's most likely going to be like 50-50 already, right? So you're doubling your throughput even more, and your non-gem kernels are going to be dominating even more further. So it becomes an interesting balancing that you have to do on how you do the scheduling. Those will increase the complexity too.
Yes, of course. You have to. It was interesting in the sense that it's a good comment to make, because we actually use the same scheduling for FP8 essentially as for PF16 eventually. So I mean, in the main repo, we use a different one, but in this refactored code, we basically use the same. So it's possible perhaps even with FP8, if you wrote a really different code path, you would get an improvement over the 1.3 petaflops I indicated. In terms of code complexity, it does greatly increase the code complexity to maintain separate methods, which is one reason for this. In this refactored code, we just unified everything in one method, basically. Yeah, so that's a good comment. I'm not even, it's possible that the FP8 improvement as it stands currently can be improved if you use a different scheduler. And definitely for FP4, you probably want to use a different one. A different scheduling idea.
So Cameron is saying it seems like the FA3 code pushes NVCC to its limits with how much more complex this is than a gem main loop. For my own work, I'm trying to implement an attention variant, modifying the main loop, and pipelining makes it hard to get good PTX. Do you have any good advice with getting the compiler to give you what you want?
Right. That's a huge issue for us, as it turns out. Maybe I'll slight digression. So FA3 is very tuned to a certain version of CUDA. So it's very tuned to 12.3. And if you look at the performance of 12.6, it's a lot worse than you might think it is. This is an issue that we're trying to solve working with NVIDIA. So we should have something to address this in terms of special binaries that NVIDIA will prepare for us. But so I would say that the way it was really a huge amount of trial and error to you can write down something which makes sense on paper, but it really was not obvious that it would actually work out the way it did. I had a very low tech way of working. I just, of course, I used the profiler. I tried evaluating I tried looking at where it was primarily stalled, and I tried running through a short list of potential overlapping schemes. But it wasn't really something that was so intelligently done, I would say. I mean, you have a few basic principles that cut down on the space of things you have to evaluate. One thing being you don't want to use many stages. You want to use like 2 in this attention main loop. That reduces the amount of things you have to think about. Like you want to use 2 stages both for the SBEM buffer and for the potential overlapping in terms of the extra register buffer. And at that point, you don't really have many possibilities. So the thing I fumbled on in the in the slide talk was there was some other overlapping that we used to do in terms of the gems and the softmax, where I overlapped well, what was it? Here I was anyway. There was a different overlapping scheme. So there were 2 things we tried. There's also a free stage pipelining thing we tried briefly. I perhaps don't have a great answer other than to just construct a shortlist based on basic principles and just evaluate them all. Maybe that's only works well for attention though, rather than your problem.
So Jay, maybe we've actually held you up a lot, but like you mentioned FA3 is like heavily tuned for CUDA 12.3. What does that mean exactly? It's just like you're basically depending on some like invis scheduler heuristics, or what does that statement really mean?
Well, at a very basic level, the performance is not very good for 12.6.
Oh, I see. Okay.
So it's there's a huge regression with 12.6, I think. So I'm not sure, I don't have detailed knowledge of the compiler. I can just observe it. But NVIDIA is providing some binary to fix this. But the point is that, yeah, I mean, you have to, the tuning process is rather laborious and maybe not so principled if it depends on things like this.
All right, Jay, thank you so much. This has been one of my favorite talks this year. So I really appreciate your time. I really appreciate technical depth. Actually, you're actually a hard person to find on social. So if people want to ask you more questions, where would you say is the best way to reach out to you? Is it your blog by any chance?
Oh, right. So probably by email.
Email, okay.
Let me just maybe put that in the chat. If I can. Yes.
While Jay answers that question, Mark, I have a question for you. What would it take for toss.compile or something to do something like what Jay has done? So I'm trying to figure out what is nirvana eventually, like after 5 years or 6 years, let's say that LLM or anything. If any time, can we see something what Jay is doing with toss.compile or any other mechanism?
Yes, so maybe I'll give a hot take answer, which is like I just don't see Jay's work being replaced by an LLM. Like I think it sort of feels like he's good at generating new tokens of information in the world. And maybe LLMs and
That's a good
compilers will
answer.
keep up. But for now, I think Jay is safe.
So there are some, I mean, maybe some of it can be automated, but there's some sort of math tricks. Like a very cool trick, as I mentioned, was realizing that instead of doing P times V, I can just do a column permutation of P times a row permutation of V. So my in-kernel transpose is not actually a transpose, in other words, and that eliminates doing any shuffles. So this is something that I very much doubt an LLM could find, or some sort of code gen could find with the FP8 implementation. It would be, I don't see how you could. Maybe for the BF16 one, it would. There's something that can be done, but not for the FP8 one.
I mean, the way I think of this is like any of these operations or optimization that you're thinking of, I don't see LLM or even toss.compile being able to do it. I'm even wondering if Triton will be able to do it either, because this requires so much customization and capability like a DSL that's so hard to build. And there's so much tight integration between the algorithm and also the optimizations that you're doing. With the underlying hardware, it's like pretty much like a hardware software core design in itself. So I don't know how any other languages or approaches will solve that problem.
Right, but I mean, there are certain tools for doing kernel fusion automatically, right?
Yes.
They can produce something. I don't know. I mean, they won't, most likely won't produce something as performant, but I mean, I can't rule it out, I guess. I don't know. I'm not
I
sure
agree. Yeah.
how advanced these tools are.
That's another question in the chat. Would it be feasible to run a scheme like Alpha Chip for any of this performance optimization? Apparently, it's what drives TPU innovation.
Oh, I don't know what. Sorry, I don't know what Alpha Chip is.
Yeah, neither do I.
I think like a lot of these efforts are like kind of describe like a hardware specification and then generate like the best kernels for it. I think this is kind of like ways out. I feel like that just seems like a harder problem.
Yeah.
Louis is also asking if the slides will be made available afterwards. Yes, give me like a day or two. I'll have the video up. And I think maybe now is like a good time to call it. Jay, thank you so much again. Next week, we have Arun Demir, one of the core devs for LM.C, who's going to be talking about PTX and like SAS optimization. So he's going very low level, and I think if you enjoyed this talk, you'll probably enjoy Arun's talk as well. Thank you, everyone, and see you all next week. And thank you again, Jay.